Hello, I am Mr. Shrum, and I am back with one of these mastery test walkthroughs. And today we're looking at periodic motion. And here we have the first question. Which quantity measures the maximum distance an object on a spring moves from the equilibrium position during oscillation? That is amplitude. Amplitude measures how far away a spring is from the equilibrium position. So think of a wave, if you will. And I will show you that. Much like a wave has an amplitude, a spring has an amplitude. Let's say a spring is hanging, and this is the equilibrium point. And if it is compressed or stretched, then you would measure how much it was stretched, and that would be called the amplitude. Or if it was compressed, you'd measure that as well. Okay, pretty easy first question. Number 2. Which is true about the total mechanical energy of a pendulum in the absence of friction? So this part is important. Without friction, energy is conserved for all positions of the pendulum. When it's at the height of the swing, it has all potential energy. And then as it swings at the most bottom point of the swing, it has the most kinetic energy. And that is all the same. The potential energy plus kinetic energy remains conserved at all positions of the pendulum. To show you what that means, I'll go for number 2. Let's say there's a pendulum and it's swinging. So here, all of the energy is converted into potential energy. But then as it drops, it's here. All that energy is converted to kinetic energy, but it's the same amount. And then once you get back up to here, that's all potential energy again. But at all of the points, the energy is conserved when there is no friction. In this, energy is conserved in this system. Okay? Perfect. So good number 2. When is the restoring force of a spring equal to 0? So remember Hooke's law. According to Hooke's law, the restoring force equals negative kx. And wow, here we go. According to Hooke's law, the restoring force of a spring is equal to negative the spring constant times the displacement from equilibrium. So another way of stating the question, when is this force equal to 0? Well, that's when the displacement is 0. And displacement is 0 at equilibrium. At the equilibrium point. Okay? According to Hooke's law. If the period of a spring is 5 seconds, what is the frequency? We're given 5 seconds for the period. I wrote this equation down here. Well, we know frequency is inversely related to the period. 1 over the period equals the frequency, or the period equals 1 over the frequency. And the units for period are seconds, and then frequency, hertz. So all you have to do for number 4, t period equals 5 seconds. Well, frequency is just 1 over t, and that's 1 over 5 hertz. And that is 0.2 hertz for number 4. All right, moving along nicely. Two springs have different spring constants. How could you identify the spring with the greater spring constant value? Well, the quickest answer is that it will be stiffer than the other. And that means it will resist you either compressing it or stretching it because it requires more force. Remember Hooke's law. F equals negative kx. Well, if one has a higher k, then it's going to take more force to move it. So more force, stiffer spring. Or higher spring constant, K, equals a stiffer spring. What is the difference between the energy of spring A, stretched 0.6 meters, and spring B, stretched 0.3 meters, if they have the same spring constant? Spring A has more potential energy than spring B. And that is the case because if you go back to the tutorial and look at the notes, the potential energy for a spring is 1/2 times the spring constant times the displacement squared. And since spring A had a higher displacement, it will have more potential energy. The more displacement, the more potential energy a spring has. I'll write it out again. 1/2 times the spring constant K times the displacement squared. More displacement, more potential energy for a spring. Okay. In Hooke's law, if a large force produces a small displacement, what does that say about the spring? Well, that means that K is large, right? If you know F equals negative KX, and you know F is large, and that equals negative KX, and you know X is small, and that means K has to be large in order for this to be true, okay? For instance, say 500, you know, the force is 500 newtons, negative K, and you know that only produced or something like that. In order for that to be true, K would need to be large. Something. That's just an example. But a small number times a large number, you need a large number to equal a large number. That's all that means. What is the main difference between the formulas for kinetic energy and gravitational potential energy? Well, yeah, B makes the most sense. Kinetic energy has to be moving, right, for something to have kinetic energy. And potential energy depends on where the object is. The higher it is, the position, the more gravitational potential energy there will be. So this makes the most sense. Kinetic, think motion. Potential, gravitational energy, think position. Potential, position, kinetic, motion. And then using Hooke's law, what happens when the displacement is tripled? Well, it's directly correlated, right? Let's stop sharing that for a second. So remember Hooke's law, F equals negative KX. Well, for that to be true, that would equal 3F, right? If F equals negative KX, and then you have negative K times 3X, you can move that around. That will give you 3 times negative KX. And then since negative kx equals f, 3f. So that means f has been tripled as well. So if you double displacement, the force, the restoring force will double as well. If you quadruple it, it will quadruple as well. Displacement is directly related to the restoring force of a spring. And last question, which amusement park ride utilizes periodic motion? So in the lesson, we talked a lot about swings, right? So pendulums have periodic motion. They go back and forth, back and forth. Springs, they go back and forth, back and forth. But in this case, the giant swing has a periodic motion. And that is it for today. I hope that periodic motion mastery test walkthrough helped you understand a few of the concepts more. And if you need more practice, go back over these and see if you can solve them yourselves. And that is all. I will be back with more lessons, and I will see you guys later. Bye.